Okay, let's deal with these tests for independence. This is a second test, sort of a sister test to the goodness of fit test. Remember, goodness of fit test is distinguished from all the prior hypothesis tests that we saw in that rather than comparing or trying to make inferences about population parameters, goodness of fit test and the test for independence makes different types of inferences about population distributions. And in this case, in the case of the goodness of fit test, what you're doing there is you have some expectation about a distribution within a population. You take a sample of that population and look at the distribution in that sample. And the goodness of fit test asks whether or not those two samples are the same, just really in the same way that other hypothesis tests work. Test for independence is a little different, and let me get into it rather than try to make a little bit more sense as we get an example out in front of us. So all we're going to do in this, I hope, brief video is to learn the meaning of a two-way contingency table, because that is how data in independence tests come at you, as two-way contingency tables. And then we're going to learn how to conduct a test for independence by hand. But just like the goodness of fit test, the calculator is going to do the work for you. The difference being in this case, I think you saw how easy in the previous video, how easy it is to get through a goodness of fit test. It's easy to get through a test for independence as well too, but it's going to make use, that test is going to make use of parts of the calculator that you use only for the, that we in statistics use only for tests for independence. Take a little bit more time. I think I'm going to put that off actually until the mastery problems. So that's what's coming. Let's get started. Back to goodness of fit. Goodness of fit data came at you, or problems came at you, as one-way contingency tables, which were some type of variable, a row variable to be sure, which had some number of categories. The first one you saw was flavors of a soft drink: cherry, strawberry, orange, lime, lemon, I think were the 5 categories in that case. And the table was really just one way, in as much as there is just a set of values against that one so-called row variable. Two-way contingency tables add a second or third or fourth row variable, so that there's actually sort of a column variable, if you will, and a row variable. And here's an example right here. This is an example in which the row variable is handedness, right hand or left hand, and the column variable is sex or gender, male or female. So you've got male and female down the side, right and left-handed along the row, so-called row variables and column variables. And you've got some data here, and so you can just sort of sit back and let this run over you, and you can see, I think, that what's going on here is there have been 100 people surveyed in some sense, 100. 52 of them are male, 48 of them are female, 87 of them are right-handed, 13 of them are left-handed. What we're going to do with this contingency table is ask, is there a relationship between the row, the column, and the row variables? That is, does the left or right-handedness depend on whether or not you're male or female? That's the key word, depend. Are they independent, or is there some relationship between them? Well, that's a pretty cool thing, right? So let's take a second example here and look a little bit more closely. In this case, in this two-way contingency table, again, there's always a row variable. This one is high or low salaries. And there's a column variable. This is you have a bachelor's degree or you don't have a bachelor's degree. So you can see what we're trying to get at. We're trying to get at, is there a relationship between a high and low salary and having or not having a bachelor's degree? Now, if you look at this data, if you look across the row that says, yes, I have a bachelor's degree, Of the 30 people in that row, 24 have high salaries, 6 have low salaries. Yet if you look in the row below, no, I do not have a bachelor's degree. Of those 70 people, 54 have a low salary, 16 have a high salary. So it would seem that this data is trying to scream out to you and say, hey, there's a dependency here between the type of salary you have and the type of degree you have, and that's absolutely true. It's it's not a one-for-one relationship, but in general, higher paying jobs require higher degrees. So there's the problem. Let's now ask, how the heck do you deal with this problem? And I'll go back to goodness of fit, because goodness of fit had this observed sample distribution to which we compared to an expected distribution. That expected distribution came from you, or at least it was given to you in the problem, right? It is your expectations. And in the same way, associated with this two-way contingency table of observed data, there's some expectation, right? Either you have an expectation that there is no relationship whatsoever, or you have an expectation that there is a relationship. So you have to produce, in fact the calculator will produce for you, but you have to produce the same type of data in terms of your expectations. So let me show you how that's done here. In particular, let's look at one box. Let's ask, how many people would you expect to be in the category of salary low and degree yes? You can see it in the upper left-hand corner of that little data matrix. Out of 100, so out of 100 people, how many would you expect? Expect is sort of the key word, to be in the category salary low and degree less. Well, one way to answer that, not really answering it, is to say, well, it's 100 times the probability of having both a low salary and having a degree, right? If you could calculate that probability times the number of people is the expectation value. So, okay, now I just got to go calculate a P low and yes, right? I have to use the multiplication rule, yeah, in order to do that calculation. And that multiplication rule says P low and yes is P yes times the conditional probability of P low given P yes, right? So we're right back to the probability theory that we thought we left back there chapters ago, right? So again, to go from the top, I'm trying to get an expectation about how many people ought to be in the box. I've got a low salary and yet I've got a bachelor's degree. I've tested 100 people, and so if I know that probability of being in that box, I should be able to multiply that by 100, and that would be the number of people in the box. How do I calculate that? The multiplication rule says P low and yes is equal to P of just yes times P of low given yes. Now, you really just have to go back to the definition of conditional probability. But here's the rub. If these two factors, having a high or low salary, having or not having a bachelor's degree, if they're independent, then this probability of P low given yes, P of low given yes, if those are independent, then that probability is just P low, because if they're independent, then whether or not you have a high or low salary doesn't depend on whether or not you have a bachelor's degree. And so that means that the probability of P low and yes times 100 is just 100 times the probability of P low times the probability of P yes. And those things you can calculate, because out of 100 people, we see that 60 had low salaries, 40 had a high salary. So the probability of having a low salary is 60 out of 100. And likewise, the probability of yes is 33 out of 100, since there are 33 yeses and 70 no's. And so I can actually calculate that probability and multiply it by 100. And when I do so, I get 18, and that's exactly the entry in this expected table. And you fill out the other row and column entries in exactly the same way. All right? Again, I want you to see where that's coming from. I want you to see that it actually involves the multiplication rule and the definition of independence within that multiplication rule. But in fact, the way you're going to do these problems is you're going to enter the observed data into the computer. The computer is going to calculate this second matrix, this expected matrix, if you will, and it's going to then do the test for you. What do we mean by doing tests? We mean very much what we meant when we had goodness of fit. Goodness of fit had a row of observed data, a corresponding row matched, if you will, of expected data. In the same way, you've got not a row now, but a matrix, a little rectangular grid of numbers that are observed, and a corresponding matched rectangular grid of numbers that are expected. You're just going to take the matched pair, subtract one from the other square, divided by the expected value, add those all up. Exactly in the same way that you did with the goodness of fit test. And again, we're really going to do that after we go through one full-blown example here where we do it by hand.